Hello, thank you for having me at Code Dive. This is pretty cool. I've never given a talk at a cinema before. I feel like Peter Jackson finally getting to show Lord of the Rings on the big screen. Fantastic. So really this talk is about refactoring your code with your own Clang tools. But I thought the imperative of this title was also quite nice. So put up your hand if you know what Clang is. Okay, so that's almost everybody. Clang-tidy. Keep your hand up if you know Clang query. And if you have ever tried to make your own refactoring tool with Clang-tidy and failed, keep your hand up. All right, so it's actually quite difficult, and this talk is dedicated to those people who have tried to use Clang-tidy to make their own refactoring tools and failed. So, this suddenly does not work. Okay, so yeah, you may have seen me around the internet for various reasons. I did a lot of work on KDE PIM. I did a lot of work on Qt. I created modern CMake. And more recently, for the last few months, I've been working on Clang itself, on Clang-tidy mostly and Clang query. So this talk is about what you can do with Clang query, with Clang-tidy, and how you can extend it, and what tools you can use to help you extend it. It's also about the problems you might encounter and tips and tricks along the way to help you succeed instead of failing. What I'm not going to cover is why you would want to do this mechanically. I'm assuming that you can understand that if you have a lot of code, you don't want to change it by hand. I'm also not going to cover the minor details of Clang-tidy, all of its command line arguments, for example. And I'm not going to talk about compilation databases. You're going to need to know about compilation databases, but there are other resources available to learn about those. And what I want you to take away from this talk is that large refactorings are possible in your code base, so in large code bases, for your bespoke needs. So even if you think that you've got some aspect or some design of your code that is suboptimal, and you might think, well, we can't change it, it touches everything. That's not true, you can do it. I also want to show you that the tooling for this is improving as time goes on. I'm working on it, and I know 3 other people are regularly making very interesting patches to the tooling in the last few months. So things are getting a lot better very fast. I'm also going to show you how you can collaborate with your colleagues when making tools like this. So recently I've been blogging. Sorry, one more thing I want to say. I work in Dublin in Havoc, and that makes me a Microsoft employee. But the stuff I'm going to show you, the new tools, that's a personal endeavor. It doesn't reflect in any way on what Microsoft is doing or what Microsoft is working on. It's not what I do in Microsoft. So recently I have been blogging about Clang tooling on the Microsoft Visual C++ blog. This talk doesn't really overlap much with those blogs, so I would encourage you to go and have a read of those after this talk. I also blog on my personal WordPress site from time to time about Clang tooling. So, getting into the tools, Clang-tidy, as it ships to you already, contains over 200 checks to either warn you about something in your code or actually change the code for you. These checks are usually a bigger deal than what Clang, the compiler, would do for you itself, because they might be more expensive to compute, for example. You can read all about them, but the reason that there's so many is that some of them are library specific. So some of them are only related to Boost, for example. And because Clang-tidy has no plugin system, those checks have to be upstream in the Clang-tidy tool itself. So you need to sort of read through them and figure out which ones might be useful to you. That's going to be the ones with modernize at the beginning of the name, the ones with readability at the beginning of the name, and the ones with bug prone at the beginning of the name. So here's a piece of code. We're going to look at what the modernize use override check does in clang-tidy. Here's a piece of code. Does it pass code review? No, it doesn't. Why? Because it doesn't use the override keyword, and it has a redundant virtual keyword. So removing the virtual keyword and adding the override keyword is exactly what clang-tidy would do for you. So let's have a demo of that. Yeah. So I have that main file, and I run clang-tidy checks equals modernize, if I can spell, use override, and main.cpp. And clang-tidy tells me you need to remove that virtual keyword and you need to add the override keyword. Now, if I run clang-tidy with -fix, it tells me it has changed my code for me. So if I then cat the file again, you can see that the virtual keyword is gone and override is now there. Cool. So that's what it does for you. You don't have to do it by hand. And you can't do this kind of thing with a regular expression in sed or Python or anything like that. You need semantically aware tools so that you can know that some particular syntax is a method. It's on a class which derives from another class, and that other class has a virtual method of the same name. So that's what you do with clang-tidy. Now, recently, as in just last week, the compiler explorer developers decided that they like clang-tidy too. Sorry. And they added this feature to Compiler Explorer. So I'm sure you've all used this tool before, but if you now go and click the, click the Add New menu and then clang-tidy, I can do this again. Checks equals and I didn't do that right. Hold on. So then I get the same output on Compiler Explorer. Now, this is useful if you want to just explore what's possible. We're not interested in the assembly. But if I go here and write int star p equals 0, you might think, well, that shouldn't be 0, it should be null pointer. So you can go here and modernize, use null pointer. And it should be showing something, but it's not. Welcome to demos. All right, cool. So that's clang-tidy. Let's move away from that now. So that's only available currently on the Godbolt beta website. You don't get to see that in the regular Godbolt yet. So our motivation is large-scale refactoring of C++ using semantic knowledge of what the code is telling us. We want to automate that. We want to have it be repeatable, so that we can put it into a continuous integration system, for example. And we want to make sure that we're not going to break any code. We want to make sure that it compiles after our refactoring so that we don't have to be too hands-on. So the way that you create your own refactoring tools is to follow a process like this. You create a new check in clang-tidy itself, because there's no plugin system. You decide what you want to port, you create a matcher query for that, and you implement a fix-it. So I'm going to be taking you through all of those steps in this talk. So to create a new check, it's very simple. Demos are always awkward. Cool. So yeah, I go to my clang-tidy directory in my source. So I've gone and cloned and built all of Clang and clang-tidy. And if I run the add new check script at the top and give it a directory name or a category and a name, I'll say add awesome prefix. It says, okay, I've done that. And it has generated some code for me. So let's have a look at what it generated. So what we have here is a method called register matchers. That's a virtual method that we're overriding. And we have another method called check. Inside the register matchers method, we have this thing, function decal. This is actually a matcher. It says, I want to do something with every function declaration that we find in the source code. Then in the check method, we bind each function to the name x. I'm actually going to change that because I find it a terrible name. I'm going to change that to add awesome prefix. So later in the check method, we go and we get the function decal itself out of our result set with that name. And if it doesn't already start with the text awesome, we add the text awesome at the insert location, which is the location of the match declaration. So I'm going to show you later, you can do insertions of text, you can do removal of text like we did with the virtual keyword, and you can do replacement of text. So this function decal, this is a little embedded DSL, a domain-specific language that you have to write inside of your clang-tidy check. And the problem is you need to figure out what is the API, what's allowed, what's available, and how does it all work. But first you need to identify code that you want to port. So you're going to want to port function calls, functions, classes, instantiations of classes, templates, etc. But unlike the check that I just showed you, you're not going to want to just add an awesome prefix to every function. You're going to want to match particular things and change them. For example, if you have a method called get on one of your classes that you want to rename to create, you need to be able to match that method on that class and not all of the other get methods, which are fine. So you'll match those entities by name or by signature or by return type or parameter name, parameter type, anything at all. Anything that's part of Clang's understanding of your C++ code, you can match on. And you do that with the matcher query. So we've already seen one of those. That was the function decal query. That's what we call a predicate language. So inside of function decal, I can add another condition, and I can say is inline. And that means I'm only interested in the function declarations which are inline. So if those are the ones that you want to port, maybe you want to make them not inline anymore. You can also say, I want to port function decals which have a particular name or which match a particular name. So that's a regular expression if there's many functions you want to change. And here I'm showing how to match a function declaration whose 0th parameter has the name foo. So you might have int foo in your function declaration. So there's a discovery problem there. The content of those matchers refine the call. It is readable, but it's not very easily writable. So, you can read cxx method decl is override, and you can understand in English what is that trying to do. And there's a lot of matchers already available in Clang. You can see them all here. No, actually we can't. So this is the list that you get if you Google that. And you do get documentation for each one if you click on them, but there's a lot to take in, and if you've never seen this or something like this before, or if you're not familiar with Clang internals already, or if you've never written a compiler before, this is a lot, and it's actually too much. There's really a problem of discovery in learning how to write AST matchers and use them. So the way you get around that is by using Clang query. So let's have a look at what that does. Sorry. Okay, so I have a source file which has 3 functions in it. And I'm going to run some queries on this. So you can see that one of them is called foo, one of them is awesome bar, the other one is called bat. So I write Clang query funcs, and I get an interpreter. So I can say, help, and I get some documentation, and I can write m and function decl. So you can see that I'm getting code completion here as well. And I can say D for decl and complete that. And now I'm getting code completion for things that can go inside of function decl. So I've shown you already that if you have a cxx method decl, you can use is override on that. But that only makes sense if you have a cxx method decl. If you have a variable, override doesn't mean anything. So we get code completion. We can scroll through them as well, actually. And so if I go has name, I can say foo. And I'm getting a result of just one function. If I just run function decl on its own, I get 3 matches, 1 for each function in my source file. Cool. So, but if I'm interested in the function foo, I can keep doing code completion, but now I'm doing code completion by value, not by type. So previously, the code completion that I was getting was allowing me to write has name, because that can be written inside of a function decl. But there's no way of knowing what the name is. But once I've completed this far, I can keep doing code completion, but I'm getting it for this exact match. So I can say parameter count is, and it's completed 1 for me, because foo has 1 parameter. Cool. So that's kind of one way of discovering what matchers can go inside of each other. Another way is you can say enable output, and I'm just code completing that, matchers. And now when I match each function, I'm getting a list of matchers which I can put inside of that. Some of them have additional bindings, which we'll look into later. But you can see it says has name foo on this one, and parameter count is 1, returns an int. And in the next match, awesome bar, it returns a float, parameter count is 0, has name awesome bar. Cool. So this is just showing you all of the matchers that you can put inside of what you've already written. So that's a good way of discovering them. It also shows you where sub-matchers match. So here I have has parameter as a matcher. And I can put that in. So I'm going to disable the that output for now. So now I have one match with two bindings. So the ID binding is the parameter, so I'm going to rename it. And the root binding is the function decal itself. So this interpreter is quite handy. I can jump between brackets. If I'm inside of a bracket, I can jump to the bracket as well. And I get highlighting of which bracket I'm under as well. So that's a nice improvement on what we used to have with Clang query. This kind of code completion also didn't used to work on Windows, but now it works on Windows. Cool. So that's Clang query. That's all we need to know about that for now. Another new development is something that I did last week. And that is I added Clang query support to Compiler Explorer. So here I have a function, and I can say add new tool Clang query future. That's a future version of Clang query. And I can start typing I can start typing matchers. Sorry. And in the result window then of Compiler Explorer, if I could show you, you get the same content. But this is something that's going to be up online. You can create something and say to a colleague, hey, my matcher doesn't work. I don't know why. Just put it into Compiler Explorer, send it to somebody else, and they'll send you a new link with a working setup. So that's a nice development. Cool. So Clang query allows you to do inspection of the code in a semantic way, in a way of using those matchers. It shows you what matchers are available, and it shows you the Clang AST. I didn't show you that, but it is kind of important, so I think I will. So I still have my session running. And I can say, well, I can match the same thing, but I can say enable output AST. And now I get a dump of the AST node for what I've matched. And that is important because it shows me that this function declaration contains a binary operator, for example. And if you remember, this is just a function which has a multiply in it. So if I want to know what else, well, this shows me what else I can match, because anything in the AST tree I can match on. So I can say binary operator, and I'm getting two results for both of the uses of binary operator in this file. And again, I can enable matchers and see what else I can do with those things. Enable output matcher. And I can say the left-hand side is a call expression, the right-hand side is an integer literal in this case. And in this case, the left-hand side is a decal ref expr. We'll get more to that later. Cool. So, unfortunately, a bunch of the features that I've just shown you are not available to you yet because I haven't upstreamed them to Clang query yet. But I'm going to try to. There's concerns about backward compatibility and all of that kind of thing, but we'll try to make it happen. Currently, today, you need to just find out what matchers you're supposed to use by examining the Clang AST. So you would tell Clang query that you want AST dumps of all the results, and then you would see a binary operator in there and kind of look that up in the documentation, see what you can use that with, etc. So it's quite a bit harder currently than it really should be, but let's see if we can improve that. There's also a few traps Let's look at this one. A few traps that result from how Clang query works today. So here I now have two Clang query panes in my compiler explorer. This one is the future one. This one is Clang query trunk. And they're matching the same thing. They both just want to match a method decal. On this side, you can see the output that you would expect. It's just showing me the one method decal which exists in my code, which you can't see now. But with trunk, you will get how many? 4 matches. And the reason for that is it's showing you implicit destructors that the compiler is adding. And it's showing you implicit copy constructors and move constructors and everything like that. Because they're not in your source code, you probably don't need to see them because you can't rewrite anything about them anyway, right? If you wanted to add a destructor, you would just do that by looking for the class itself. Another example is, I'm not on the internet. Another example is templates. So here I have some quite simple template code. And I have one instantiation of that template. That's all that's in this class. And I'm instantiating it with the type int in the second parameter. And that's then used in a type def. So if I'm looking for the type def declarations, what I want is a type def is a result which shows me that the type is if true, because that's what's actually used in the code. But currently, Clang trunk will give you a bunch of results, one of which is telling you that the type of this type def is int, because that's part of the instantiation of the template. So if you would try to use the clang-tidy tool, modernize using instead of type def, you would actually rewrite this with using type equals int because of that template instantiation. And then your code won't build anymore because you probably use this template with other types. So that's just a trap that you can fall into currently with Clang query trunk or clang-tidy trunk. Hopefully we'll get to fix that. But it's a backward compatibility concern, obviously. All right, so once you've written your query and you know that you want to match methods called get on the class myFactory, you need to know how to replace the source code which relates to that match. So every Clang AST class has a bunch of locations associated with it, and an instance of that class can return to you the location for various parts of that AST node. So in this case of function decal, I'm showing you 3 different locations that are available for you to access. Get begin lock, get location, and get end lock. And you might look at this and think to yourself, okay, if I want to replace the return type of this function with something else, all I need to do is get the word at get begin lock and replace it with something else, maybe safe int or long int or anything. But then you would come across this and you would say, oh, well, the return type isn't at the get begin location anymore. And it turns out, you can just about see that actually because it's cinema. It turns out there's this long expression that you can use in order to get the correct location of the return type for a function declaration. How can you discover that? It's quite difficult. There's also source ranges in the Clang AST classes. So the get source range will return you everything from the beginning of the function declaration to the closing brace, so which might be on a different line. And if you want to get just the function signature, there's this longer expression that you can use. You get the type location object and get the source range of that. And if you want the parenthesis range, there's this very long expression that you can use. So once again, we've got a discovery problem here, right? How can you know, given some source code that you're looking at, what location expression do you need to use to match on that? So once again, we can use Clang query to find out. So this is good enough. I can just enable output source location and run any matcher. And now I'm getting a list of all of the source locations and ranges, for each match in my source code. So get begin lock points here for this expression, get expr lock points to the plus, and get end lock points to the end. So I see get source range as well. And I can do that with anything that I match in the Clang AST. So here I have the bat function, which returns double, and I can see all of the locations that could be what I need in order to match on a particular place, because I want to replace it. So you can see in this first hit, get begin, there's very many locations, expressions which I can write in order to get that first column. Get begin lock doesn't semantically sound like what I want, because it's not telling me that it's anything to do with the return type. But here, get return location, get begin lock is actually what I want. So you need to look through this list of results and see, okay, what's semantically what I want here, and pick that expression. It's also relevant to note that anytime you have get end location, anytime you access that, it's actually going to give you a location for the beginning of the last token. So that can be confusing sometimes, but if you actually do replacements, Clang will forward that to the end of the token, and it'll do the right thing anyway. It'll do what you expect. But if you're looking at this output, you might be confused by seeing that the end location is at the beginning of the token. Oh. Let's look at a few more examples of that. So, array sizes. So here I have a small C++ source file again. And you can see that I'm creating some arrays, and the way that I'm defining the size of each variable is different each time. I'm just doing that for demo purposes. So I can get a result for each one of them by saying var_decl. And it's showing me that it matches on each line. And I can say enable output source location. And for example, if you look at what am I looking for? This one. This kind of complicated expression. I have 2 plus 1. And you might wonder, well, how do I get the plus for that? And it's this big long expression. So you have to go through the array type lock. But it's telling you everything that you need to know. Another case is templates. So at the bottom of this file, you can see that I have a very long return type for this function. So if I run Clang query on that, and match that function declaration, I can say enable output source location, and for any location inside of that return type, it's showing me a highlighted caret pointing to whatever I need to get to. So this is it's a lot of data. But it used to be that you didn't get this kind of data at all. This is just new in my Clang query fork, I guess, which I'm trying to upstream. you would just kind of have to read the documentation to figure out that you have to write these expressions. So I'm just trying to improve that situation a little bit. And of course that works as well on Compiler Explorer. So the nice thing about using Compiler Explorer to do this is actually get highlighting in the source of compiler, in the editor of wherever the location is as well. So hopefully that'll get upstream as well. So yeah, let's just briefly look at the source code again. So here's this new check that I created at the beginning of the talk with the script. We have the matcher. So now you know what a matcher is and where to put it. And down here we have a diagnostic creating an insertion at this location. And now you know how to get locations and what locations are relevant and how to find which locations are important for your check. But that's only part of the problem. If you have a large amount of code and a large amount of source files, you can't be processing them all one by one in order to do a refactoring like this. One of the problems is if you consider what happens when you give a source file to clang-tidy, it's actually going to process the header files as well, because that's where your declarations are. And the problem is if you change those header files and then move on to the next CPP file, you'll find that it doesn't even compile because you've already changed the header. So you don't want to do that. Instead, you need to put all of the changes that you encounter into a database and then use the Clang apply replacements tool to actually change your source code. So that ensures that everything gets refactored while it still compiles, and then after applying the replacements, hopefully it still compiles. But you don't have to do that yourself. There is a tool called run clang-tidy in the Clang source tree as well. It actually runs clang-tidy in parallel. So if you have 8 cores, you'll get 8 clang-tidies in parallel refactoring your code. You can give it a pattern so that it'll change only specific files, and it handles that deferred replacement that I mentioned. So it puts everything into the database, and then it uses Clang apply replacements to apply those. So that's nice, but let's think about it even more. So when I said that the changes actually go into a database, what that means is some YAML files on your file system. It's not a SQL database or anything. It's just a directory where you put all of the replacements in the form of YAML files. So you have a tool. Into it, you put a C++ file that processes headers, and out of it, you get a YAML file. If that sounds familiar, you can kind of compare it to your compiler. So you have a compiler, that's your tool. You give it a C++ file, and you get out of it an object file. So if they're so similar, what does that mean? How can that benefit us? So as you might have guessed from my slide, one of the things we can do is we can do our refactoring with Ninja. All we need to do is generate a Ninja file, and because I'm a CMake guy, I use CMake to generate my Ninja files. But I've done it in a very hacky way using CMake. Maybe we can come up with some better way of generating these Ninja files. But, so I override the compile object variable within CMake to run clang-tidy, essentially. And, well, if you do this with CMake, it's warranty void, like you're not doing the right thing with CMake at all. And if you tell anybody I told you to do this, I will deny all knowledge. But, let's see if it works. So I've already generated this build system, but so I'll just run it. So this is how you generate a compile database with CMake. You just run CMake with a special variable set, and it should do it. If you don't write a typo. Cool. So something is wrong. This didn't happen when I was preparing, but let's just see if regenerating that thing fixes the problem. And it seems to. So Ninja is now running my clang-tidy check, which adds an awesome prefix over the entire LLVM and Clang source. For each change that it makes, it's outputting all of this content. And you can see that there's a lot of it because it's happening 8 times in parallel. But that doesn't really give us anything that we didn't already have by using the run clang-tidy tool. But what it does give us is Ninja features. So I can run this command to generate a trace file from the Ninja log, and then I can open that in Chromium. So if I go here to about tracing, and hit load, I can load that trace. And it shows me a visualization of the refactoring as it happened. Maybe that's useful, maybe not. I mean, you can see which files take a long time to process. If you're running multiple refactorings, you can see what refactoring is very slow and maybe optimize it and make it faster. So that's kind of cool. Maybe there's lots of other tools which work with Ninja, which become available if you use Ninja to do your refactoring. But that's not all. So those of you who were in Victor's talk just before mine will have heard him speaking about build distribution. So that's where you compile your object files using your compiler on all of the other computers in your network. And usually that works by passing a C++ file and the compiler over to those remote computers, doing the compile there, and sending the object file back to you. So let's just send clang-tidy over instead, and let's get a YAML file back instead of an object file. Should be pretty easy. The only thing I actually had to do was rename clang-tidy binary to clang++ and have it output files called obj, which still contain YAML. So the build distribution tools expect the compiler to be called a certain name, and they expect the output to be called a certain name. So once I renamed those things, I'm able to do refactorings with Icecream. So if you've never used Icecream, you won't recognize this, but this is the Icecream monitor tool. This shows that Marvin has been sending jobs out to these remote computers, agent 1, 2, 3, and 4. So they're doing my refactoring for me. So let's see if I can demo that as well. So here's my Icecream monitor. I've actually set up four Docker containers so that this emulates a kind of network. And this is going to be difficult. Let's put that over here. Right. And now if I run Ninja, you can just see it lighting up. So it's sending those refactoring jobs to my remote, Docker containers. Each time a ring lights up, it's doing a job. And if it's got multiple rings, it's doing multiple jobs at the same time in parallel on that computer. And I'm getting a lot of output from Icecream here because I've set debug mode. But what it's actually doing is it's populating a fixes directory which contains YAML files. So that's what they look like. It's just a bunch of text saying that at this location we need to insert the text awesome. Cool. So that's Icecream. So now you're able to create your own clang-tidy checks using clang-tidy and clang-query. You're able to scale your build by distributing it on your network and by using your build tools. There are still some other build issues. And again, if you're at Victor's talk, you will have heard of Unity builds. Because these refactoring steps all need to process the headers. Unity builds really help you get the compile time down and the refactoring time down. Same with pre-compiled headers and distributing your build. One thing to keep in mind, though, is that if you want to do refactoring like this, you need to make sure that all of your generated files are generated. So if you're doing a Qt project, you need to make sure that you have all your mock files generated. Or any other generator that you use. Otherwise, the refactoring will fail because the build would fail. So that's all about tools. On now to the tips, tricks, and traps part of this talk. As you're doing your discovery and learning about AST matchers and the AST classes, you should kind of focus your refactoring attempts on the expressions because you have a lot more of them. So you might have just, one function decal that's interesting, but you will have many call expressions which call that function. So say if you want to change the name or the signature of that function, you're going to have to change all of the call expressions. Usually you would, types are easy to handle because all you do is you use string matching to say which type is relevant. So in this case, class free, easy. So I mentioned call expressions. That is given by the call expr AST class. Oops. And here's a call expr in this source code. And here are all the function decals in that source code. Cool. But when you're writing your query, you want to say, I want to match the call expression whose callee is that function decal. So I might write call expression callee function decal has name bar, and that would match this call to bar. So the callee matcher is the thing in the middle which makes that happen. Same with variables. So decal ref expr is an expression which references a decal, refers to a decal. So here are all the decal ref exprs that I would find if I match them in clang-query, and here are all the var decals or parameter var decals in the source code. And again, I need to relate one to the other. So I would say, give me all the decal ref exprs to var decal. So instead of call E, I'm writing 2. And then I would match on something interesting about that var decal, its name or its type or the function that it's in or anything. And finally, member expression. So here are the member expressions in this source. Here's the only field decal in that. And if I want to match member expressions which refer to field decals, I need to use the member connector. So here's a table just summarizing the last 6 slides or so. Depending on the AST type that you're interested in, you use a different traversal matcher to get to its declaration. And you almost always want to get to the declaration because the call expert doesn't know the name of the function that it's calling. It just has a pointer to this function decal. So you need to follow that pointer and check the name. Another trick that you might want to use is optional matching. So if I have a record decal, and that means a class or a struct, which has a method called foo, I might write something like this. And I want a binding in my result set for both the method and the class. Great. But what if I want to match all classes with some condition? And I also want to capture the methods conditionally. So if the method is there, I want to capture it. Otherwise, I still want the class. And to do that, you would write something like this. You would use the any-of matcher. So that combines any matchers that you give it. And if any of them pass, you still keep the result. So in this case, I say I want any of either the method or anything at all, which just means it's optional. And what I do then in my check implementation is I check to see whether I actually have that method in the result set, and then I do this or I do that. So you can conditionally change things depending on what's there. But, this is kind of a lot of boilerplate code that you might not want to write. Instead of doing all of that, you could create your own matcher that you can use in your queries. So this will only work in your C++ code. You won't be able to use this in Clang query, for example. But in your own matcher that you write, in your own check that you write for clang-tidy, you can write this kind of lambda expression, which will make whatever matcher you give it optional. And you would use it in quite a natural way. So you just say, here's my record decal, and optionally, I want to match that method. If there's something about any AST classes which you want to match on, but which there's no matcher upstream for yet, you can make your own matcher for them. So if you look at the source code of the AST matchers, you'll see a lot of macros. Here I'm using AST matcher. And I'm giving it a name is static data member. And all that does is it returns true or false, right? These are all predicates. So I just have to return something. And then I can use it just like any built-in matcher. So you can create your own matchers for checking attributes on functions or anything else you need to do. So again, thinking about the case where you have, say, 100,000 lines of code, you might not want to change everything at once if you're doing a large refactoring. So if you can imagine, changing some function signature, you might end up with a diff of 10,000 lines, a patch or a commit of 10,000 lines. And that's not really good because it's hard to review. And even if you can build it locally, it might fail on CI. And if you have any experience with that kind of thing, sometimes unit tests will fail on CI and they pass locally for you. And if that's the result of a small patch, usually you can figure out why. But if it's a 10,000 line of code patch, it's going to be very difficult to figure out why something bad is happening, why some unit test is not passing. But also, sometimes patches have to be reverted, and not immediately. So if you commit your 10,000 line patch, and then 6 weeks later you have to revert it, you're going to get a lot of merge conflicts. And that is not easy to handle. So often what you want to do is, I call it sharding. So break your refactoring into multiple different pieces. Titus Winters calls this non-atomic refactoring, which might be a better name. And what you might do is you might say, okay, I need to replace a type. Say we have a string type in our code and there's a better string type. That means that you have to migrate all of your function declarations, your function return types, your function parameter types, any fields and any variables in your code base which use the old string. So you can change all of those one at a time. So you can have one patch which only changes the local variables, etc. But there are a few traps that come out of that. So in this case, if I change the S string from my string to your string, it won't compile anymore because the bar function takes it by reference and it expects the my string type. So in that case, I have to change the parameter type and the variable type at the same time. Here again, if I want to change the type of the field, m_s from my string to your string, that might not compile either because maybe getString is returning that member, or maybe not. You can't really tell just by looking at the header. So, you sometimes have to massage things a little bit in order to make them build if you're doing this kind of thing. And finally, a virtual trap. So if I have multiple libraries and I decide I'm just going to migrate one of them, and it contains the class called derived, and it uses the class called base in some other library which I'm not touching, and it implements foo. It re-implements foo. And I want to change function parameters. I can't actually change this one because it's a virtual override. It won't build. So you have to handle that kind of thing as well. So here you would write method decal unless it's an override. So there's a matcher built in for that. Finally, there's a performance trap in this. If it is strings that I'm porting away from, or between one string type and another, you will have to do conversions. And with string conversions, that can actually get quite expensive. And if you do a lot of it, because your refactoring is only partly done, you can get into a performance trap there. So that's something just to keep in mind. Finally then, the final trap that I'm going to show you is the special function trap. So if you decide that you want to refactor this kind of code, A == B, you might say, okay, well, what's the matcher for that? Well, it depends. It depends on the type, because that changes how == is implemented. If the types are both int, then it'll be a built-in binary operator. But if you've got structs, say, with their own member or non-member == function, that'll be different. So you've got to handle these cases with different matchers. In the case of the built-in ones, you just use binary operator, has operator ==. That'll work. But if you've got structures, a struct with a member == operator, you need to use the CXX operator call expression, and that has overloaded operator name. So it's just a very different syntax. It's kind of unfortunate that that's so divergent, and it's something that you'll encounter if you try to do this kind of refactoring. But it actually doesn't make a difference if the thing is a non-member function. You can still just use the same matcher for that case. All right, so my time is up, but here's my summary. You can use clang-tidy for your own bespoke code transformations. So anything that you can imagine, you can actually do it. You'd use Clang Query to help you do that. That's the tool for discovery, because discovery is the biggest problem when you're trying to write a clang-tidy check. discovery of AST classes and nodes, discovery of matchers, and discovery of locations. So Clang Query helps you with all three of those. Use the reference to see what else is available. Use your build tools and build distribution network in order to speed things up. And you can really make major changes in your code base very fast. So again, the takeaways, better tooling, better collaboration are coming. And yeah, you can do this. So if you want to play with the Clang Query stuff that I showed you in this talk, you can get that at ce.stevera.com. I encourage you to read my blogs on the Visual C++ blog if you're interested in this talk. And do use the Stack Overflow tag for Clang AST matchers if you have any questions. I'll keep an eye on that and answer anything that I can. So, are there any questions?
So, I think maybe somebody... Okay.
Just a question about this clang-tidy. Is it possible to get some data from one CPP file, for example, the implementation, and use it in the other checking in clang-tidy? For example, I want to get every function which has operator dots there, or operator or multiplying inside, and I want to, in every other file, I want to use it differently.
You can do anything with scripting if you can imagine a way of storing that information, like between steps. Nothing is built into clang-tidy for that.
Okay, so but you can somehow enforce the order of files, or
no, you would have to do it in 2 steps yourself. You know, you would have to figure out how to do that. Yeah.
Okay.